All right, we're going to go ahead and get started with Chemical Reactions 4. This podcast is on how to predict products for single replacement reactions. So you've learned to identify all these types of reactions, but now you're going to learn that not all of these reactions actually occur. So take a moment here and jot down some of these rules, and also go ahead and find this handout here on the activity series of metals. This was referenced in podcast 1. You were asked to cut it out and tape it into your composition notebook. So if you could get that, we're going to be using this throughout the podcast. All right, so not all these reactions occur. When you encounter a reaction that is not favorable and will not occur, we're going to just simply refer to that as no reaction, or NR. And in order to predict this for single replacement reactions, you have to look at something called the chemical reactivity of the substances. And that is simply the tendency of a substance to undergo a chemical change. When we look at this activity series of metals, it's pretty intuitive the way it's set up. Basically, the reactivity is going to be decreasing as you move down the series. In other words, species at the top are going to be the most reactive and are going to have the greatest chemical reactivity. So we're going to look at some examples together, and I'll explain this a little bit more. I also wanted to point out that there is a reactivity series for halogens as well. These can all be explained using atomic theory, bonding, and periodicity, which are topics that will be covered later in the course. Okay. Our first example here. Solid magnesium is mixed with aluminum chloride. As always, take a moment, pause the podcast, go ahead and write this out. And we're going to predict the products. That's what's different now. You're given the reactants and asked, what do they produce? Okay. So in this case here, we're going to look at the two cations, the two metals. This is the activity series of metals. We're going to compare magnesium to aluminum. Whichever one is higher up is the more reactive species. So when we look at this here, let's see, they're very close to one another. Magnesium is higher than aluminum. Magnesium is more reactive. So magnesium is able to come in and essentially kick out the aluminum. That's going to leave aluminum by itself as a solid, and then magnesium will combine with the chlorine. Now what you need to look at here is you need to be smart about how you're balancing these new formulas, okay? So in this, excuse me, here we had aluminum. Aluminum had a +3, and that makes sense that there's a subscript of a 3 on the chlorine, which carries a -1. Now, magnesium, when it reacts, is going to carry a +2 oxidation state. So when you write this new binary compound, you're going to have 2 chlorines for every 1 magnesium. Then you have to go through, as you learned in previous podcasts, and place coefficients in front to ensure all of the atoms on the reactant side are balanced with the atoms on the product side. Okay, now, if I were to reverse this, all right, take a look, compare these two. If I were to reverse these two, this reaction does not occur. And the reason for that is aluminum is not as reactive as magnesium. Aluminum is not going to be able to come in and kick out magnesium. So when these species are mixed together, there is no reaction. Now, students a lot of times will also ask about, okay, what about if I write the ionic compound before the metal? Does the order matter? And the order of the reactants does not matter at all. It does not play a factor in this. Okay, let's do some examples here, and I want you to go ahead and try this one out. We have iron 3 chloride is mixed with solid lithium. Iron 3 chloride. Iron 3 chloride is mixed with lithium. And the question is, does the reaction occur? We'll take a look at this. Lithium is at the very top of the activity series. So it is the most chemical reactive species that we have. So yes, lithium is going to come in and grab chlorine. Now lithium is a +1, chlorine is a -1, so we're going to have aqueous lithium chloride being formed. And now we have solid iron. Okay, now let's go ahead and balance this. 3 chlorines here, 1 here. So we'll put a coefficient of 3 in front of lithium chloride. That'll give me 3 lithiums, so I'll put a coefficient of 3 in front of lithium, and we are all balanced here. All right, so our next example here, phosphoric acid is combined with solid calcium. Okay, so 8 is ich, 8 is aus. Let's see what we have here. Phosphoric, 8 is ich. Well, you should know a polyatomic phosphate. 8 is ich, so this makes sense. Phosphoric acid. So let's see if we can figure this one out. Phosphate -3. So I am going to need 3 of those guys. All acids are aqueous as combined with solid calcium to yield, if it even occurs. So we're going to find these guys on our reactivity series. Calcium is much higher than hydrogen. So what we're going to see here in this case is calcium is going to come in and kick out the hydrogen. All right. So we're going to form calcium phosphate, aqueous, and hydrogen. Hydrogen gas, Brinkelhoff, please don't forget that. It's one of our magic 7. It's diatomic. And so now let's go ahead and balance. We have 3 here, so I'm going to start and put a 3 in front of calcium. We're just going to see, here's a family of phosphates, 2. Let me try to slap a 2 here. That gives me 6 hydrogen. If I put a coefficient of 3 here, we end up with 6 hydrogen there. All right, so example number 3 here. We have solid iron reacting with aqueous nickel 2 chloride. Let's get that one started here. Solid iron reacts with nickel 2 chloride to yield something, maybe. So we'll come over here and I'll put a little dot here next to iron. And we'll see a couple below here. We have nickel. Okay, so the question is iron the more reactive species? And the answer is yes. So iron's going to come in and kick out nickel. That's going to form. Now, one thing you do need to pay attention to is the particular ions formed. In this case here, this is going to form iron 3 chloride. And nickel is going to get kicked out, and aqueous. And so let's go ahead and do place some coefficients in here and see if we can get this balanced. Let's see here. So first off, I see my chlorines here. I'm going to need to make those 6. Now I have 2 iron, so I'll put a 2 there. And now I have 3 nickel, and I'll put a 3 here, and double checking, this is all balanced. And in our final example for this podcast, we have aqueous lithium bromide. is mixed with solid tin to yield. All right, so wait a minute. Lithium is the most reactive species, and tin is way down toward the bottom here. So there's no way this reaction is going to occur. Tin is not going to come in and kick out the lithium. So this is an example of a no reaction. This reaction will not occur. So in this podcast, we've continued to learn how to identify chemical reactions, how to balance chemical reactions. You're still getting practice with nomenclature, and now you're even learning how to predict the products of chemical reactions. You do have a new problem set that's available for you to start on. You can go ahead and get started on the single replacement reactions, and in the next podcast, you're going to learn how to predict products for double replacement reactions. Thank you.